I never imagined that a simple invitation from the army would place me at the heart of one of the most secret projects of World War II. Until then, I was just a mechanic for agricultural machinery, accustomed to the smell of grease and the lazy rumble of tractors. But, in that winter of 1941, everything changed when I was taken to an unnamed factory, hidden behind high fences and silent guards. It was there, in that icy corridor, that I realized we were about to transform simple civilian tractors into war tanks capable of deciding battles. Only many years later, as an old army boomer, did I find the courage to tell everything I saw. I still remember the cold wind cutting across the open truck bed as we drove through the hills. The canvas above us snapped with every bump, and no one said a word during the long ride. The soldiers sitting beside me stared forward with the same uneasy curiosity I felt. We had all received the same short message, stamped with an official seal. Report at once for mechanical duty. No details, no explanations, just coordinates and a time. When the truck finally stopped, the guard pulled back the canvas and told us to step out. I expected a normal industrial complex or perhaps a familiar assembly yard, but what I saw instead was something entirely different. Ahead of us was a massive steel gate with no markings, guarded by men who looked as if they had been instructed not to smile for the remainder of their lives. Instead of signs identifying the place, there were only numbers painted over thick concrete. 47B. The air smelled of engine oil and coal smoke, but there was something else mixed in, an urgency that seemed to hang over everything. A tall officer with a clipboard approached us and checked our names one by one. When he reached my name, he looked up and examined me with a stare that felt like a test. Then he simply nodded and motioned for me to follow the group. Inside, the noise increased. It wasn't chaotic, but it was constant, the kind of noise that comes from machines designed to work without pause. We walked through a corridor lined with pipes that carried steam overhead, and the temperature rose with every step. It reminded me of the agricultural factories I had worked in. But there was something more intense about this place. The security, the secrecy, the atmosphere, everything suggested that whatever they were building here was not meant for the public to know. We reached a briefing room where an engineer waited for us. He wore a worn-out jacket stained with oil, and his glasses seemed permanently fogged with dust. He didn't introduce himself. Instead, he pointed to the large drawing pinned to the wall. It showed a chassis that looked vaguely familiar, yet reinforced and altered in ways that attracted immediate attention. "This," he said, tapping the sketch with a metal pointer, "is the beginning of what will become a combat vehicle. We are taking reliable agricultural platforms and reshaping them for military use. Your experience with machinery has placed you here, and your work will directly support the production needs of ongoing operations." His voice remained calm, but the weight of the words settled on all of us. It was the first time we understood the scale of what we were being asked to do. We were no longer simply mechanics or technicians. We were now part of a program that demanded precision, secrecy, and absolute focus. He led us to the assembly floor. The enormous room stretched farther than I could see, filled with partially assembled frames, stacks of reinforced plates, crates of components, and engines arranged in rows. Overhead cranes slid across rails, carrying steel casings from one station to another. The faint echo of tools striking metal created a rhythmic pattern that dominated the space. I felt a strange mixture of excitement and apprehension. The frames in front of me still resembled the tractors I'd worked on for years, but the modifications were unmistakable. The axles were thicker, the suspension reinforced, and the hull plating laid out nearby was far heavier than anything used in farming equipment. This factory was taking familiar machines and turning them into something entirely different. A supervisor walked up and placed a folder in my hands. It contained technical diagrams, torque specifications, and a timetable that made it clear there was no room for delays. Every minute counted. The global situation demanded rapid production, and the factory had been instructed to deliver results at a pace that left no space for error. The supervisor explained that we would begin by dismantling a series of tractors on the far side of the floor, stripping them down to their essential components. The powertrains would be reconfigured, the hulls strengthened, and the platforms redesigned to withstand conditions far harsher than farmland. Everything about this process needed to be methodical and consistent. As I examined the diagrams, I realized how complex the transformation really was. The original structure of the machines provided a starting point, but nearly every part would be modified or replaced. It wasn't a simple conversion. It was a reconstruction, performed with urgency, but also with strict precision. The slightest imbalance could compromise the final outcome. When I placed my hand on the first chassis assigned to me, I felt the cold steel beneath my fingers. In that moment, I understood that what we were doing here would leave a mark on history. Even though the world outside never saw the inside of 47B, the vehicles built here would eventually move across the landscapes of conflict, carrying crews who depended on every decision made inside this factory. I took a slow breath and prepared my tools. The foreman signaled for us to begin. The machinery roared back to life, and the factory entered its steady rhythm once more. This was the moment my role truly started, inside a facility that officially did not exist, working on machines that would change the course of events far beyond these walls. When I first walked toward the center of the assembly floor, I expected to see another agricultural machine waiting for repairs. After all, most of us had been recruited for our experience with tractors, engines, or heavy equipment. But as I moved closer to the structure resting on the elevated platform, I realized I was looking at something different. It still carried the unmistakable silhouette of a farm tractor, yet its proportions had changed. Reinforced beams had been welded along the sides, and the entire frame looked heavier, as if it were preparing for challenges far beyond fields or harvest seasons. An engineer approached me and said quietly, almost as if he were revealing a secret we were not supposed to hear aloud. He explained that what I saw was the early foundation of what would later become the M4 Sherman tank, a model that would eventually be produced in large numbers. At that stage, however, it was simply a test platform, a hybrid of familiar agricultural machinery combined with new adaptations designed for durability and mechanical stress. I stepped closer and placed my hand on the cold surface of the frame. The metal felt rough, still carrying traces of machining and welding. The suspension components were more robust than anything used in farming. The engineers had been experimenting with different configurations to determine which could best support the weight of armor plating and a rotating turret. Every part of this early structure reflected trial and error, a process driven by necessity. The need to accelerate production meant that the project relied on what already existed in the industrial landscape. We were adapting proven mechanical foundations to meet urgent requirements. The engine compartment revealed another set of modifications. The original tractor engines had been replaced with a provisional mount designed to fit radial engines or other available power plants. The engineers explained that several prototypes were being tested to evaluate torque output, fuel consumption, and reliability during extended operation. These trials were essential because the finished vehicle would need to move reliably across difficult terrain. It could not be slowed by overheating or inconsistent performance. That was why the team continually adjusted airflow channels, repositioned vents, and reinforced mounting brackets. One detail that struck me was the improvised nature of the early armor mock-up. Sheets of metal had been bolted to the sides of the frame, not as final components, but as placeholders to test weight distribution. Each sheet had markings showing stress points recorded during earlier vibration tests. When I asked about them, the engineer told me that these markings helped identify where the frame needed strengthening. It was a reminder that every bolt, plate, and weld had to serve a purpose. Nothing could be left to chance. As I continued inspecting the structure, I noticed the early tracks laid out beside it. They were not yet the standardized tracks used in the later Sherman production lines. Instead, they were assembled from existing materials sourced from different suppliers. The engineers told us that the first goal was simply to create a moving platform capable of carrying significant weight. Only after establishing consistent mobility would the team focus on refining the final track design. This approach allowed the project to progress quickly while still performing essential tests. Another supervisor walked over to brief us on the challenges the team had faced with steering adjustments. The original tractor steering mechanisms were not designed for the kind of directional control required for a tracked combat vehicle. The engineers had experimented with differential braking systems and clutch controls to allow smooth directional changes. These early systems were still far from perfect, but they formed critical steps toward the eventual steering mechanisms incorporated into later models. I could see how every new attempt brought the project closer to a functional design. While standing beside the prototype, I felt both admiration and apprehension. The adaptation process demonstrated remarkable ingenuity, but it also highlighted the limitations we had to overcome. Many of the components in front of me represented solutions built under intense pressure. Supply shortages forced the engineers to make do with what they had, and manufacturing deadlines influenced nearly every decision. This environment demanded constant improvisation while still maintaining rigorous standards. The workers had to rely on precision, despite the relentless pace. The engineer then guided me around the frame to the spot where the turret ring would eventually be installed. At that moment, only a reinforced circular opening existed. It was positioned with extreme care to maintain balance and structural integrity. He told me that the rotating turret mechanism had been one of the most challenging engineering problems. The system needed to support the weight of a fully armed turret while remaining stable during movement. The early mock-up served as a testing foundation to evaluate rotation smoothness and ensure that weight distribution did not place excessive stress on the frame. Before leaving the platform, I took a moment to observe everything once more. The unfinished structure represented more than mechanical experimentation. It symbolized the transition from civilian machinery to a completely new purpose. Each component reflected decisions made under urgent conditions, but always with precision and responsibility. I understood then that our work would continue shaping machines that would eventually be deployed far beyond the walls of this facility. The supervisor told us to prepare for dismantling, reinforcement, and reassembly procedures scheduled for the next day. As I walked back toward my station, I carried with me the realization that we were not simply adjusting machines. We were participating in a transformation that would influence future operations. The prototype, in the center of the factory floor, was the beginning of a process that demanded discipline, focus, and respect for every detail. That understanding stayed with me long after I left the platform that day. The true pressure of our work revealed itself in the weeks that followed. The early prototype had shown promise, but it also exposed every weakness we still needed to address. Each test, each vibration reading, and each engine trial added new tasks to an already demanding schedule. The supervisors reminded us daily that production timelines were not flexible. Every hour mattered because the global situation was shifting rapidly. It became clear that the factory's mission was not only important, but urgent. The atmosphere inside the building reflected that urgency. The machines operated almost without pause, and the assembly lines ran through long shifts. The engineers had divided the factory into specialized sections so every team could work simultaneously. One group reinforced chassis frames, another calibrated engine mounts, another tested suspension components, and another performed repeated inspections. The coordination between these sections had to be flawless to maintain the required pace. I quickly learned that delays in a single department had consequences that spread across the entire facility. One morning, for example, a shipment of reinforced steel plates arrived later than expected. That single delay forced the welding teams to adjust their sequence of work, which then affected the engine installation timeline. The supervisors gathered us and reviewed new schedules that compensated for the interruption. It was a constant challenge, but everyone understood the importance of keeping production uninterrupted. My own responsibilities increased during that period. I was assigned to oversee part of the reinforcement process for the central hull section. This area required careful alignment because it supported several components critical to the vehicle's operation. The engineers had designed precise measurements that we needed to follow, and even minor deviations would compromise stability. Each shift involved rechecking measurements, tightening bolts, and verifying weld quality. Every step required focus and accuracy, even when fatigue made concentration difficult. One aspect that surprised me was the level of documentation required. Although the facility operated under strict secrecy, the technical records were detailed. Each modification, each component test, and each reinforcement procedure had to be logged. These records ensured consistency and made it possible to track the results of design changes. When a new adjustment was introduced, we had to compare previous notes to understand how the structure responded. This process allowed us to refine the vehicle continuously, even as deadlines approached. The engineers also held briefings to update us on progress. During one meeting, they explained that the vehicle needed to withstand long operational periods without mechanical failure. That meant we had to anticipate real-world conditions. Dust, mud, sudden temperature changes, and extended engine use were all factors we had to consider. The suspension system, for example, had undergone modifications. After early tests showed it needed more stability under heavy loads, these adjustments required additional reinforcement work, adding hours to our schedule. Even so, the engineers insisted that the long-term reliability of the machine could not be sacrificed. Another challenge involved the powertrain tests. The engines available at the time had different performance characteristics. The rapid pace of development meant that the engineering team had to evaluate which type could offer the best combination of power, reliability, and fuel efficiency. During the testing period, I assisted in setting up components for temperature and stress evaluations. Sensors were placed at key points around the engine to measure heat distribution, vibration intensity, and mechanical strain. These readings helped determine whether certain configurations could withstand extended operation without failure. Despite the pressure and long hours, the work environment fostered cooperation. Skilled technicians from different backgrounds worked side by side, sharing insights and solutions. Some had experience with tractors, others with heavy industrial machinery, and others with mechanical design. Together, we created a rhythm that allowed us to tackle challenges quickly. When a part showed unexpected wear during a test, someone always had an idea for a reinforcement technique or adjustment. These exchanges kept the pace steady, even during the most demanding days. As the weeks passed, the prototype began to resemble something far more advanced than the machine we had first encountered. The hull grew stronger, the suspension more stable, and the engine configurations more consistent. Each improvement brought us closer to a functioning vehicle capable of meeting the expectations placed upon it. Still, the supervisors reminded us that every step forward brought new tasks. The moment one challenge was solved, another took its place. That was the nature of accelerated development. I recall one evening when I stayed after my shift to finish recording measurements. The factory was quieter, but the machines continued running in the distance. I stood beside the reinforced hull and thought about how much had changed since my arrival. The pace had transformed us. Even though exhaustion was common, the commitment shared by everyone in the facility kept us moving forward. We were not simply assembling a machine. We were building something that would carry responsibilities far beyond its steel frame. The next phase of development promised even greater complexity. The prototype would soon undergo more demanding trials, and our schedules would tighten further. Yet as I walked out of the factory that night, I understood that the race against time was the very reason this facility existed. Every bolt tightened, and every measurement recorded brought us closer to the goal that had been set from the beginning: to create a reliable vehicle in the shortest time possible, with precision guiding every step. The day the first turret prototype arrived at the facility became a turning point in our work. Until then, everything we had assembled felt like a vehicle still tied to its origins as an agricultural machine. The reinforced hull, the suspension adjustments, and the engine trials all represented progress, but they remained components of a machine that could have served many functions. The arrival of the turret changed that. It signaled that the project had crossed into a new phase, one that required an entirely different level of precision and coordination. I was assigned to the team responsible for evaluating the turret ring assembly. The engineers explained that this component was critical because it supported the rotation system and maintained structural stability under mechanical stress. The early model we received consisted of a circular ring reinforced with evenly spaced support points. It had been designed to maintain balance while carrying a structure mounted above it. My task began with examining every connection, verifying alignment, and ensuring the ring was level. Even a slight deviation could create long-term operational issues. As the mechanics lifted the turret onto the ring using an overhead crane, the atmosphere shifted. Everyone knew that this was not simply an additional component, It was a defining element of the vehicle's identity. The turret was heavier than I had expected, constructed with reinforced plates designed for structural rigidity. At that stage, it did not yet contain additional components, only the outer shell and the internal framework. Still, its weight demanded careful handling. Once the turret was secured, we performed the first rotation test. The engineers instructed us to move slowly, listening for irregularities and watching for signs of friction or imbalance. Turning the turret required controlled motion at first, and the early rotation was uneven. The mechanism hesitated, then moved forward again. The engineers paused the test and marked several points for adjustment. The surface beneath the ring showed minor signs of uneven pressure distribution, indicating that the frame required further refinement. For the next several days, we made repeated adjustments to the ring. We replaced bushings, repositioned rollers, and recalibrated spacing. Every change required another rotation test. The more we worked, the smoother the motion became. The engineers monitored each attempt and recorded the results. Their notes highlighted improvements in stability, pressure distribution, and rotational consistency. These details helped guide the next set of modifications. During one of the tests, I stood close enough to hear the faint sounds coming from the mechanism. At first, the turret produced a low, steady tone as it turned. Then, for the first time, it completed a full rotation without hesitation. The movement was controlled even and predictable. The engineers signaled for another test at a slightly higher speed. Again, the turret performed without issues. That moment marked an achievement that had taken countless hours of effort. With the basic rotation established, the next phase involved reinforcing the interior. The engineers installed support structures inside the turret to simulate weight distribution. These internal additions affected balance, requiring further refinements to the ring. We conducted additional tests, each one monitored closely. Some adjustments involved tightening connection points that had loosened under repeated motion. Others required reinforcing sections to withstand prolonged use. One challenge we encountered was vibration transfer. During faster rotations, the energy from the movement caused subtle vibrations along the hull. The engineering team identified the source quickly and introduced new reinforcement brackets beneath the ring. These additions distributed the force more evenly and reduced the vibration to acceptable levels. It was another example of how interconnected every component was. Solving one problem often revealed another, and each change needed to be documented carefully. Another critical part of the process involved testing the structural durability of the turret. Although we were working with a prototype, its design needed to support significant stress. The engineers simulated repeated operational movement by rotating the turret through long intervals. These sustained tests revealed points of potential wear, especially where components connected to the ring. Reinforcing these areas required precise measurements and repeated evaluations. During these extended tests, I often remained on the factory floor longer than my shift required. Something about the transformation felt significant. I watched as the turret moved, every rotation marking another advancement in our work. The engineers reviewed graphs and notes, comparing performance across tests. Their attention to detail reinforced the importance of precision. No error was too small to correct. Eventually, the prototype reached a point where the turret rotated with consistent stability. The engineers recorded the results, marked the improvements, and prepared the documentation for the next stage of development. We were told that additional components would soon be added to the turret, requiring further adjustments. It was clear that this achievement was not an endpoint, but another step in a long and demanding process. Walking away from the platform that evening, I reflected on how far the project had progressed since my arrival. The early frame had seemed incomplete, almost improvised. Now, with the turret in place and functioning, the machine stood much closer to its intended identity. The addition gave the vehicle a distinct purpose. It moved us beyond simple mechanical adaptation and into the territory of precise engineering. The following day, new tasks awaited us. The turret project had proven that progress could be achieved through persistence, careful adjustments, and teamwork. As I prepared to continue my role in the development, I understood that each advancement brought new challenges. Still, seeing the turret complete a full rotation for the first time remained one of the defining moments of my time inside the facility. I remember the morning when the factory floor felt different. The usual rhythm of metal presses, riveting guns, and conveyor clanks was still there, but the air held a kind of tension that reminded me of the moments before an inspection. Except this time, the pressure did not come from officers or administrators. It came from us. We were about to see whether months of work, improvisation, and long nights would become something real. The tractor-to-tank conversion project had reached its first true test, the prototype's initial movement. I walked into the assembly hall and saw the machine resting in the middle of the floor. Even without paint, without markings, and without some of its armor plates, it already felt heavier than a tractor had any right to be. We had replaced the original agricultural frame with reinforced side beams, added suspension elements adapted from designs used in pre-war military vehicles, and mounted a pair of widened tracks built from a mix of new steel and repurposed industrial components. Everything was experimental, and everything had been argued about at least a dozen times. I stood close to the left track and ran my hand along the metal. It had taken us weeks to get the track shoes cast evenly. The steel quality varied because wartime restrictions forced the factories to reuse whatever material was available. Each batch had to be adjusted manually. I could still remember the night shift when a misaligned mold ruined half the run, and we spent hours grinding each piece back into usable shape. When I looked at the track now, I saw those hours of work embedded in every bolt. The engineers gathered beside the hull. Most of them had arrived with experience in farm machinery, not armored vehicles, but they learned fast. They carried notebooks filled with sketches, performance charts, and calculations checked so many times that the pages were thin. The head engineer gave a signal to start the preparation. The fuel crew wheeled in the drums and began filling the modified engine. What had once powered a plow had been reworked until it produced enough torque to move the heavier frame. It was still an experiment, but on paper it should have worked. When the driver climbed inside, the hall went silent. I knew him from previous tests on agricultural prototypes. He had a calm personality that made him perfect for this kind of moment. He closed the hatch gently, as if he did not want to disturb the machine's concentration. The engineers checked the lines once more, confirmed the lubrication points, and stepped back. The engine turned over with a rough cough. A few workers flinched at the sound, expecting a stall, but it steadied into a deep mechanical rumble. The vibrations traveled through the concrete floor and into my boots. The smell of warm metal and fuel spread through the area, familiar yet heavier than usual. It was the scent of risk, of effort, and of a machine taking its first breath. We watched as the driver increased the throttle. The engine growled, and a burst of exhaust escaped the rear. For a moment, nothing else happened. The tracks remained still. The engineers leaned forward, ready to shut everything down if something failed. Then the left track shifted slightly, almost hesitant. A second later, both tracks began to roll. The hull lurched forward by a few centimeters. That was all we needed to know. The machine could move. A wave of quiet relief passed through the group. No one shouted or clapped. Wartime factories were not places for celebrations. Still, I felt something close to pride. Months earlier, this had been a simple tractor frame, pulled from a storage yard. Now it was a functioning prototype for an armored vehicle that could support our soldiers. The movement test continued. The driver maneuvered the machine across the hall, increasing speed in careful increments. We listened for any irregular sounds. If the gears slipped, we would hear it. If a suspension element bent under pressure, we would notice the change in vibration. The engineers marked every observation in their notebooks. At one point, the machine hesitated while turning. The right track produced a sharp clatter that echoed through the hall. We motioned for the driver to stop immediately. The engineers crawled under the hull and confirmed that one of the tension components had shifted out of alignment. It was a manageable issue, expected in early prototypes. They made temporary adjustments and signaled for continuation. The machine completed the next phase of the test with fewer problems. Watching the tracks grip the floor and push the heavy vehicle forward gave me a deeper understanding of how much transformation our factory had undergone. We had spent years building equipment for fields, not front lines. Now the same workers who once assembled harvesters were creating armored hulls, welding protective plates, and testing engines designed for entirely different environments. The transition had not been smooth, but it had been necessary. The head engineer eventually raised his hand, signaling the end of the test. The driver powered down the engine, and the hall returned to its usual chorus of distant machinery. The silence around the prototype felt almost respectful. We knew the work was far from finished. The armor still needed reinforcement, the powertrain required improvements, and the weapon mounts had not yet been installed. But the foundation existed. The machine could move under its own power, and that meant progress. As we gathered our tools and prepared for the next phase, I realized something. This prototype represented more than mechanical engineering. It showed how quickly people could adapt under pressure. None of us had planned to build tanks. Most of us had never even worked near military technology before the war. Yet we had taken a civilian machine and reshaped it into something capable of supporting a battlefield. That transformation mirrored our own. We were learning, adjusting, and becoming part of a larger effort. That night, when the factory lights dimmed and the halls emptied, I walked past the prototype one last time. It rested quietly, its metal still warm. I placed my hand on the hull and felt the weight of what lay ahead. More tests, more revisions, and more long hours. But for the first time I felt certain that we were building something that mattered. The tractor had become more than a machine. It had become a symbol of determination and adaptation, shaped by the hands of workers who understood what was at stake. And this was only the beginning. When the movement tests ended, we shifted to the most demanding stage of the entire project. Adapting real armor onto a frame that had never been designed to carry it. Turning a tractor chassis into a functional wartime vehicle required far more than simply adding steel plates. Every added kilogram changed how the suspension behaved, how the engine worked under strain, and how the frame absorbed vibrations. If we miscalculated, the machine would fail long before reaching any battlefield. That reality stayed with us during every shift. The first challenge was securing steel of consistent quality. Wartime shortages made uniform production nearly impossible. Some shipments arrived with small variations in composition, and we used testing equipment to measure hardness, flexibility, and structural stability before cutting anything. The steel was originally meant for industrial equipment, not armored vehicles, so we adjusted each plate through heat treatment and controlled cooling to increase durability. Even then, some pieces warped slightly and had to be reworked. Nothing was wasted. Once the plates passed inspection, we began shaping them for the hull. The bending presses strained to handle the thicker material. Bolts and rivets had to be recalculated for shear strength, because a plate that detached under vibration could damage the entire vehicle. Welders worked in long shifts, maintaining steady lines across the joints. Many of them had previously welded agricultural machinery, where precision mattered, but not at the same level required here. They adapted quickly, learning how heat dispersion changed when working with thicker steel. I spent most of my time helping measure impact angles. Armor was not only about thickness, it was also about placement. The more sloped the plate, the better it could deflect incoming damage. Our engineers studied diagrams of existing armored vehicles to understand how to maximize protection without exceeding weight limits. We angled the front plates and reinforced the sides while keeping the top lighter to reduce overall mass. Every adjustment was recorded, tested, and rechecked. The assembly hall grew noisier as the plates took shape. Sparks flew from cutting wheels, and the sound of hammers striking steel echoed across the floor. Despite the intensity, we worked within strict safety and procedural guidelines, ensuring the environment remained controlled and suitable for heavy manufacturing. Coordination mattered as much as craftsmanship. If one team misaligned even a single plate, the entire structure could shift off balance. We installed the lower hull plates first, securing them tightly to the frame. Once those were in place, we added internal braces to manage vibration and structural stress. The original tractor chassis did not include reinforcement for armored loads, so we created a network of cross supports that helped distribute weight. As the hull grew heavier, the prototype's suspension responded with visible compression. We monitored that carefully, recording how each stage affected ground clearance. The side armor required additional work. Tracks created constant vibration, and any loose plate or unstable mount could threaten safety and reliability. We drilled new mounting points, secured reinforced bolts, and added welded seams along the edges. When the final side plates were installed, the machine no longer resembled a tractor. Its profile had begun to resemble a small, armored vehicle, compact and practical for its intended role. The turret posed another challenge. Our factory had no prior experience building rotating weapon mounts. Instead, we designed a simplified structure, a small, reinforced compartment with a manually operated rotation system. It was not as advanced as those found in full-scale military vehicles, but it served the purpose required for testing. The engineering team machined the base ring with extreme precision, ensuring the rotation remained smooth. Any irregularity would have caused jams or uneven stress on the armor. As the external plates were completed, we shifted to interior adjustments. The added armor reduced internal space, restricting movement for the crew. We reconfigured the seating, instrument placement, and access points to maintain usability. Ventilation also had to be improved. The engine generated more heat when pushing a heavier load, and the internal air had to circulate efficiently. We added vents that directed airflow through safe, reinforced channels. By the end of the second week of armor installation, the machine had gained significant weight. We recorded every measurement and compared it with the vehicle's performance calculations. The numbers showed that we were pushing the limits of the modified tractor engine, but still within acceptable operational margins. This was a relief, though we knew real-world testing would reveal more than any chart could. The first static stress test took place one early morning. The hall was quiet except for the mechanical devices used to measure pressure and flex across the hull. We attached sensors along the plates and applied controlled load increases. The machine settled under the weight but held steady. A few attachment points needed reinforcement, but there were no signs of structural failure. That result boosted morale across the factory. After the test, I walked around the hull, checking the welds and brackets. The metal was cold beneath my gloves, smooth in some places and textured in others where we had reinforced seams. Standing beside the machine, I could no longer see the tractor it once was. The transformation was almost complete. The vehicle had gained presence, substance, and a quiet authority, as if acknowledging the purpose it had been built for. What struck me most was how everyone, from engineers to welders to mechanics, had contributed to that transformation. Each plate, each bolt, and each piece of the frame carried evidence of problem-solving and determination. We had taken a civilian machine and given it new identity and capability. That process reflected more than engineering. It showed the adaptability of ordinary workers placed under extraordinary demands. As the shift ended, the head engineer announced that the next phase would involve mobility tests under weight. If the machine could move smoothly with its new armor, we would advance to field simulations. The announcement stirred a mix of anticipation and concern. Armor installation was one thing. Proving its functionality under real conditions was another. That night, when the hall lights dimmed, I stayed behind briefly and looked at the armored hull resting quietly. It stood heavier and more resilient than before, shaped by long hours of work and careful calculation. Tomorrow, it would face its next challenge. Whether it passed or failed would depend on every decision we had made over the past weeks. I took a final breath, stepped back, and prepared myself for what was coming next. The morning of the first full-weight mobility test felt more tense than any earlier stage of the project. Up to that point, our work had been confined to the factory floor, where every movement could be controlled, measured, and repeated. Now the armored prototype would move under its own power for the first time with its complete hull, turret, reinforced frame, and fully loaded suspension. If anything failed, the consequences would be immediate and costly. We all understood the risk, yet there was a sense of pride too. We had reached a moment that no one in the early days of the project believed possible. The testing area behind the plant was a long stretch of packed dirt, surrounded by industrial equipment and storage facilities. It was far from a battlefield, but it allowed us to evaluate traction, balance, and engine strain without external hazards. Before the prototype moved, we checked every bolt and weld one last time. I walked along the side of the armored hull, running my hand over the metal surface. The plates were solid, and their angled alignment gave the vehicle a sturdier presence. Nothing rattled, nothing shifted. That was a promising sign. The engine crew performed warm-up procedures, listening closely to the sound of the motor as it adjusted to the load. The tractor engine, though reinforced and modified, still carried its original character. It produced a low, steady rumble rather than the sharper roar of a purpose-built tank engine. We had to make sure it could handle the torque demands of the heavier machine. When the engine settled into a smoother rhythm, the lead mechanic gave a signal. I climbed onto the hull to observe the suspension as the vehicle prepared to move. The driver, a veteran mechanic who had tested heavy machinery for years, sat inside the cramped compartment. The interior was tight, and the new armor restricted visibility, but he understood the layout better than anyone. The testing supervisor stood several meters away, clipboard in hand, and raised his arm to begin. The prototype lurched forward slowly, its tracks gripping the dirt with firm pressure. At first, the movement was stiff, and the machine seemed unsure of its own balance. The weight distribution pushed the suspension down, and we watched carefully to see if the frame would overflex. But after a few meters, the vehicle steadied itself. The tracks adjusted to the ground, the suspension smoothed out, and the engine found its rhythm. The machine continued forward at a steady pace. We followed alongside at a safe distance as it completed its first pass down the track. Dust rose behind it, forming a light cloud that hung in the air. The engine temperature increased slower than expected, a sign that the cooling system improvements were working. The vehicle reached the end of the track and turned with deliberate force. The turning radius was wider than ideal, but manageable for the size and power available. The driver brought the vehicle back toward us, maintaining a consistent speed. Now that it was moving, its behavior resembled that of early armored tractors used in previous military experiments. It was not fast, but it was stable. The sight impressed me more than I expected. We had taken a machine born for the fields and given it a controlled, strong movement under armor. It demonstrated that improvisation combined with engineering discipline could create something functional. After 2 more passes, the machine underwent stress tracking. The driver accelerated slightly, pushing the engine further, while the suspension absorbed the impact of small bumps and uneven ground. The hull vibrated, but did not show signs of structural weakness. Welds remained solid, and the mounting points for the armor plates stayed firmly in place. We scanned for cracks, distortions, or signs of overheating. None appeared in the initial rounds. Next came the incline test. The far end of the testing ground had a moderate slope that allowed us to measure traction and load distribution under elevation. The driver approached the hill at a reduced speed, and as the tracks engaged, the extra weight of the hull became instantly obvious. The engine strained, but did not falter. The tracks dug slightly into the dirt, finding grip. Slowly but steadily, the vehicle climbed the incline and reached the top. Standing at the base of the hill, I felt a mixture of relief and admiration. The reinforced chassis held. The load-bearing calculations were correct. The track alignment did not shift under pressure. The machine had conquered a challenge that even a few weeks earlier seemed uncertain. When it descended, the controlled weight transfer showed that the suspension system was stronger than many had predicted. Once the incline test ended, the vehicle returned to the flat ground for braking evaluations. This stage was delicate. A heavy armored vehicle required predictable stopping behavior. Too much forward shift on braking could stress the front plates or cause track tension imbalance. The driver accelerated slightly and then applied gradual braking. The machine slowed evenly. He repeated the test with a firmer stop, and again the vehicle responded within expected margins. The stability during deceleration was better than some engineers had hoped. After the final movement, the engine was shut down for a full inspection. The mechanics opened panels carefully, allowing the heat to escape before reaching inside. The oil levels, coolant flow, and pressure readings all aligned with the expected values. No leakage, no burning smell, and no signs of internal stress. The modified tractor engine, while not designed for armored combat, had handled the loaded test admirably. I walked around the hull one more time. The dust clinging to the armor gave the machine a rugged appearance, almost symbolic of its transformation. The plates were still secure, the seams unbroken. The turret mount had not shifted even slightly during movement. Every detail that we had agonized over for weeks had proven itself in a few hours of controlled testing. When the supervisor called us together, he announced that the mobility test was officially a success. We would proceed to extended endurance runs over the coming days, followed by operational assessments with additional crew simulations. The news sparked quiet satisfaction across the team. The project was not complete, but it had passed one of its most critical milestones. As the vehicle rested in the fading daylight, I felt a sense of connection to the entire journey. From the moment we received the order to convert tractors into armored vehicles, we faced challenges that demanded both creativity and discipline. Seeing the prototype move confidently under its own weight reminded me why ordinary workers, given responsibility and purpose, could achieve remarkable results. The machine had proven itself capable. Now we would push it further. Endurance testing began 2 days after the successful mobility trials. By then, our team had inspected every component twice, tightening bolts, cleaning the track assembly, recalibrating gauges, and verifying that the engine mounts had not shifted. Even with all that preparation, we understood that endurance trials revealed weaknesses no factory inspection could detect. The prototype would be pushed for hours rather than minutes, and anything overlooked would surface quickly. Endurance was not merely a test of machinery, it was a test of everything we had built so far. The testing ground had been expanded for this phase. The engineers created a loop consisting of packed dirt, uneven surfaces, loose gravel, and a shallow water crossing. These conditions reflected what early armored support vehicles might encounter in unpredictable terrain. The goal was simple: keep the machine moving while measuring stress, temperature, vibration, and structural stability under continuous load. Before dawn, I stood beside the hull as the driver prepared for the long run. The cold air condensed against the steel plates, forming a thin layer of moisture. When the first rays of light hit the armor, the vehicle looked heavier than ever, shaped by weeks of labor and constant adjustments. The mechanics primed the engine, checked the coolant levels, and monitored pressure indicators. Once everything aligned, the supervisor ordered the start. The engine roared to life with a steady, controlled rhythm. The driver eased the vehicle forward onto the loop. At first, the prototype moved as smoothly as it had during the previous tests, but endurance trials required more than short bursts of performance. As the machine continued its first lap, we followed in a support truck equipped with monitoring instruments. From inside the truck, I watched the prototype's tracks carve a defined path in the dirt, the suspension absorbing repeated vibrations. During the second lap, the engine temperature reached its normal operating range. The cooling system held steady, and pressure remained within acceptable margins. What concerned us more was the behavior of the track tension under continuous movement. Tracks naturally loosened as they warmed and expanded, so the mechanics watched the readings closely. By the fourth lap, the tension increased slightly, but remained stable. That was a promising sign. The gravel section created the first significant challenge. The rocks shifted unpredictably beneath the tracks, causing stronger vibrations than those felt on dirt. The hull shook, but nothing rattled, and none of the plates emitted signs of stress. When the driver checked in by radio, he reported that visibility inside the compartment was reduced due to dust, but manageable. Airflow adjustments we had made earlier kept the interior free of excessive heat. On the 8th lap, the machine entered the water crossing. The water was shallow but enough to test the lower hull seals. As the vehicle pushed through, the tracks churned mud and water outward. We watched closely to ensure no water seeped into critical compartments. When the machine emerged on the opposite side, the mechanics inspected it briefly and confirmed that the seals held. The drainage channels we had built performed exactly as intended. After an hour of continuous movement, the engine noise changed subtly. It was slight, almost unnoticeable, but enough for the seasoned mechanics to detect. The support truck radioed the driver to reduce speed while we checked the readings. The oil temperature had risen slightly beyond the initial projection, though still within a safe margin. We recorded the change and continued the test. Endurance trials required accepting wear patterns, provided they did not threaten system integrity. By midday, the machine had completed dozens of laps. Dust coated the hull, and the tracks showed the beginning signs of abrasion. The suspension, however, remained strong. We stopped the vehicle for a scheduled inspection break. When the driver opened the hatch, warm air escaped from the interior, carrying the familiar smell of heated metal. Mechanics removed access panels and checked vital components. The engine showed no leaks, the belts maintained tension, and the exhaust temperature normalized during the pause. After a short break, the supervisor ordered the second phase of testing. This time, the driver would push the machine at a slightly increased speed, maintaining that rate for an extended period. The engine responded with determination, and the tracks began to bite deeper into the terrain. The hull vibrated more intensely, but the reinforced plates held secure. Inside the support truck, we monitored every data point, ready to call a halt if readings crossed into dangerous levels. Halfway through the second phase, small issues emerged. A bracket near the left suspension mount showed signs of stress. It had not cracked, but the paint had begun to flake, revealing a shift in force distribution. We recorded the observation and prepared to reinforce the bracket once the test concluded. Meanwhile, the prototype pressed forward without slowing. The final segment of the endurance run required the driver to navigate the entire loop without support personnel following closely. This simulation was designed to test communication, isolation, and mechanical reliability under minimal supervision. From a distance, I watched the armored figure of the machine move steadily along the path, turning, climbing, splashing through mud, and returning again. Each lap carried the weight of months of planning and work. When the vehicle finally rolled to a halt at the end of the trial, the engine remained strong, its steady rhythm unchanged. The hull, though coated with dirt and marks from the terrain, showed no structural failures. The tracks, while worn, remained aligned, and the suspension had endured the strain without collapsing or bending. The entire team surrounded the machine, examining every detail with careful precision. The supervisor marked the test as successful. The prototype had completed everything required of it, and revealed only minor issues, all fixable with routine reinforcement. That conclusion filled us with a quiet but powerful sense of accomplishment. We had built something that could endure, something that had proven itself through hours of continuous pressure. As I stood beside the machine, the evening light casting long shadows across the testing ground, I understood that our creation was no longer an experiment. It had become a functional vehicle, capable of supporting tasks far beyond its original agricultural purpose. The endurance trial had not only tested the machine, it had tested us, our calculations, our craftsmanship, and our resilience. The endurance tests had confirmed the machine's strength, but the next stage demanded a different kind of scrutiny. A vehicle did not exist only for engineers. It existed for the people who would operate it. Before any field demonstration or official evaluation, the prototype needed to be tested from the inside by crews who understood armored vehicles. Even if this one was far simpler than frontline equipment, my role shifted again. Instead of inspecting plates and measuring stress lines, I was now responsible for observing how humans interacted with what we had created. The crew assigned to us included a driver, a radio operator, and a mechanic who had experience with small armored units. Each of them arrived early, ready to spend the entire day learning the interior layout. The prototype was built from a tractor base, and we had modified it heavily, but the interior still reflected its origins. Space was limited, controls were close together, and every movement required careful coordination. When the crew climbed in for the first time, their reactions made it clear that we needed to pay attention not just to engineering challenges, but to practicality and safety. As they explored the compartments, we took notes. The driver immediately pointed out that the seat position restricted visibility through the small front slit. We adjusted the mounting, raising it slightly and shifting it backward to give him more control. The radio operator examined the communication panel and asked for clearer labeling. We made the changes on the spot, adding engraved markings instead of painted symbols to ensure durability under heat and vibration. The mechanic spent the longest time inside, testing the maintenance access points. He noted which bolts were difficult to reach and which access panels required excessive force. The interior layout had been designed during late hours when our focus was on achieving structural integrity rather than ergonomic convenience. His insights gave us a new perspective, and we made several modifications. Widening an access hatch, repositioning the extinguisher mount, and creating a safer angle for the internal wiring conduits. Once the interior adjustments were noted, we moved to crew motion drills. This stage required the crew to practice entering and exiting the vehicle quickly while we timed them. For a machine intended to support operations rather than perform direct armored combat, speed still mattered. The first trial revealed how tight the interior truly was. The driver took nearly double the target time to climb out because the hatch hinge resisted movement. We disassembled the hinge, cleaned it thoroughly, and reinforced it to allow smoother operation. During these drills, I watched the crew closely. The humidity inside the vehicle rose rapidly, and even with the ventilation system functioning, heat accumulated in the turret compartment. We evaluated airflow again and modified one of the vents, redirecting it toward the lower section to improve circulation. It was a subtle improvement, but noticeable once the drills resumed. After a midday break, we initiated functionality tests. The driver practiced maneuvering, while the other crew members simulated their operational tasks. We created a simple course within the testing area, straight paths, wide turns, and a few uneven sections to test communication inside the compartment. The crew learned the rhythm of the machine quickly. Though it lacked the power of traditional military vehicles, its reliability impressed them. During one test, the driver reported that the clutch pedal felt heavier after several minutes. We examined the linkage and discovered minor friction due to accumulated dust from previous trials. The mechanics cleaned the area and applied lubricant, restoring smooth operation. This incident reminded us that a long-term vehicle needed ease of maintenance as much as stability. Communication trials came next. The radio operator tested the internal and external communication systems while the vehicle moved across the field. Vibrations often interfered with radio clarity, so we added shock-absorbing brackets to the radio mount. Once installed, the static reduced noticeably. The operator's voice carried clearly through the headset, even as the machine rumbled across uneven ground. Later in the afternoon, we conducted fire suppression drills. These were safety procedures that ensured the crew could access the extinguishers quickly and understand internal safety protocols. While the prototype did not carry weaponry that produced extreme internal heat, the engine compartment still demanded caution. The mechanic practiced reaching the suppression control, and we adjusted its position slightly for easier access. The crew then simulated long-duration operation, occupying the vehicle for over an hour while moving intermittently. This test revealed something we had overlooked. The seating cushions were too thin for extended use. They absorbed vibration poorly, causing discomfort during long runs. We made note of this and arranged for thicker padding to be installed the next day. Toward evening, we held the final evaluation of the day. The crew stood outside the hull, covered in dust and sweat, but genuinely impressed by the machine's performance. They provided final comments that ranged from control comfort to hatch operation. One suggestion stood out, adding a small storage compartment for tools and essential equipment. We discussed the modification and decided it was feasible without compromising structural balance. As I recorded their last remarks, I realized how different this stage felt compared to earlier ones. When the project began, our concerns focused on engines, steel plates, and mechanical stress. Now, we were addressing the human experience inside the vehicle. These insights mattered just as much as any engineering calculation. A machine that ignored the people meant to operate it was incomplete. When the crew left for the day, the testing ground became quiet again. The dust settled around the tracks, and the steel hull reflected the fading light. I climbed onto the vehicle once more, sitting near the turret mount. The echoes of the crew's voices still lingered in my thoughts. Their suggestions, frustrations, and moments of approval. The machine had survived mechanical trials, endurance runs, and pressure tests. But today, it had passed another milestone. It had proven itself not simply as a functioning armored platform, but as a vehicle that could support real operators under real conditions. I looked over the testing area, knowing that the next phase would take us closer to final evaluation. Every adjustment, every reinforcement, and every observation had brought us here. Now, with the crew tests complete, we were ready for the last and most decisive challenge awaiting the machine. I remember the morning we prepared the last batch of tanks, as clearly as if it happened yesterday. The factory floor felt different that day. The usual rhythm of machinery still echoed through the steel beams overhead, but there was a sense of conclusion beneath it, a quiet awareness that months of tireless work were converging into one defining moment. I'd spent so much time inside that plant that I could recognize every shift in tone, every mechanical tremor, every change in the smell of oil and warm metal. Yet that morning carried a weight unlike any before. The tractors that had arrived at the plant earlier in the war had long since been transformed. By that final month, they no longer reminded me of the agricultural machines they once were. Instead, I saw them as completed armor platforms, shaped for durability and reliability above all else. The factory supervisors had pushed for consistency in every step, reinforcing the notion that even small deviations could affect long-term reliability. I had learned to respect that discipline. At the time, I did not realize that these machines would remain important long after the war ended, studied for their engineering rather than their combat role. My team and I ran the final inspection cycle with the same precision we applied on the first day. The process started with checking track tension, especially important due to the origins of the design. Tractors were built for forward traction on soil, not for the lateral and varied forces generated during armored maneuvers. Through months of modifications, the track assemblies had been strengthened, but I never forgot how delicate that balance was. Each bolt, each reinforced link, mattered. I knelt beside the final tank in the line and checked the tension readings, noting that the adjustments had been done correctly. It was routine, but even routine actions feel momentous when you know you are doing them for the last time. From there, we moved to the engine tests. The engines had been heavily modified from their agricultural origins. They were no longer meant to run at steady speeds for long hours in fields. Instead, they had been reworked to handle rapid torque changes, higher heat cycles, and unpredictable operating conditions. I watched as the test operator started the engine. The low, rolling sound filled the room, and the vibration traveled through the concrete floor. To someone unfamiliar with engineering, it might have sounded unremarkable. To me, that sound represented months of recalibration, rebuilding, and testing. It symbolized the transformation of civilian machinery into stable military hardware. When we transitioned to the armor evaluation, I stood quietly for a moment, remembering the early days when we realized the limitations of the tractor design. The original frames had not been built to support heavy armor, and adding weight too quickly caused structural issues. Over time, we solved that by redistributing stress across the chassis and reinforcing the mounting points. The factory had become a place of constant adaptation. The final series of tanks was the culmination of all those changes, and I felt a certain pride when the team confirmed that the armor plates were aligned and secured exactly as planned. The interior inspections came next. I always checked the driver's position personally. It was a simple seat, but everything around it had been designed with function in mind. Controls were adjusted to be intuitive. Visibility was improved where possible, and the mechanical linkages were tested repeatedly. As I sat inside, I realized how many hours I had spent in similar positions, verifying every lever and pedal. The instruments were basic, yet reliable. We focused on durability rather than sophistication. That philosophy had guided the entire project. As the day went on, we completed the last hydraulic tests, evaluated turret rotation, and checked communication wiring. Each step felt both familiar and significant. I found myself slowing down, not because I doubted the work, but because I wanted to appreciate every remaining moment. The factory had shaped me just as surely as we had shaped those machines. By late afternoon, the final tank was ready to leave the plant floor. Workers gathered informally around the exit platform. No speeches were given. There was no formal ceremony. Instead, there was a shared silence, the kind that comes from knowing you have contributed to something larger than yourself. When the engine started and the tank began to move forward, its tracks clattering against the metal ramp, I felt a mix of closure and reflection. It was not triumph I felt, nor sadness, but a recognition of what effort and coordination can achieve under pressure. As the tank disappeared through the wide doors of the plant, sunlight spilled in behind it, illuminating the path we had walked countless times. The building seemed suddenly larger and emptier. I stayed behind after most of the workers left, walking the length of the factory one more time. The sounds of machinery had faded, replaced by distant echoes and the soft hum of cooling metal. The air smelled of oil and steel, the same scent that had greeted me at the dawn of every shift. Standing in the quiet, I thought about the countless hands that had contributed to the project. Engineers, welders, inspectors, technicians, supervisors. Every completed tank represented thousands of combined hours. None of us sought recognition. The work itself was enough. Even now, years later, I believe that the true story of that factory is not just about machines, but about the dedication and endurance of the people who built them. When I finally stepped outside, the evening air felt colder than usual. I looked back at the large building, its silhouette stark against the fading light, and understood that this chapter of my life was closing. But the memory of that last day, the sound of the final engine leaving the factory, and the knowledge of what we accomplished together would stay with me forever.